the topic tonight is about this dragon curve. But that's only the beginning. Actually, it's going to be about principles of doing inductive proofs and working with symbols, or let the symbols work for you, which is consistent with what I have been talking about in Flora, which is the summer school which happened for the past 2 weeks. And so the summer school is about logic, programming languages, and functional programming. And I think mainly the same principles apply to what I'm going to talk about tonight. That's why I encourage students from that course to come to this lecture. Okay, so first to start with, let's talk about dragon curve. It is perhaps the most well-known, one of the most well-known recursive curves. And so this one is perhaps a level 12 dragon curve. And how was this generated? There are actually 2 ways to generate such curves. That in the first approach, which I'm going to call the unfolding approach, we start with a single line like this, which is the level 0 dragon curve. And to go from one level to the next, we start with the previous level. And okay, also this curve implicitly has a beginning and an end. So to go from one level to the next, you make a copy of it, and spin the copy 90 degrees clockwise around the end point. And that's the level 1 dragon curve. Let's do this again. You start with this, make a copy of it, spin it 90 degrees clockwise. I zoom it on unintentionally. Okay, so then this is the level 2 dragon curves. Let's do this again. That make a copy of it, spin it 90 degrees clockwise. Why is it distorted? Okay, it should be like this. Let's do only once more. No, I missed it. This one. Right. And if I do, so if I this level is, you start to see this loop-like structure, but that's actually not a loop. So one interesting property of the dragon curve is that it's always a consecutive curve, and it never crosses itself. But however, so that's a property which I would like to learn to prove later, but unfortunately not today. So that's one of the ways to create a dragon curve. But there's an alternative way that you also start with a single line, which is the level 0 dragon curve. So I'm going to draw the previous level in dotted line like this. And then in this approach, in every step you add one turn, one crease, one fold to each of the line segments. So this dotted line is the previous level. So you instead of one straight line, you turn it into a curve, into a crease like this. And that's level 0. And okay, now this is the previous level. And to create the next one, you add creases to the lines, but however, you do it by creating one. You turn to the right once, and then turn to the left once. So it's one right, one left. And actually, when you link to the right, you actually create a left turn. And when you link to the left, you actually create a right turn, which I'm going to talk about later. But however, I'm going to erase this later. Okay, let's do this again. So this is the previous one. Okay, again, this is the starting point, this is the end point, right? So you start from the starting point, And then now this is a right turn. You go to the right, and then go to the left. Go to the right, and then go to the left. Are they actually the same curve? My drawing is bad, but they're actually not the same modulo the rotation. Okay, then I'm not going to repeat it again later. So actually, the thing is, there are lots of interesting properties about dragon curve, which I'd like to explore. But tonight we're going to talk about only one thing: how do I make sure that these two approaches of drawing the curve actually give me the same curve? And one of the ways to explain that is this. Actually, this is probably how dragon curve actually came from. That you take a piece of paper and you fold it like this, and then fold it again like this. Keep folding again. I cannot fold it too many times. But I always fold toward the same direction. When you unfold it, actually, the shape you get is the dragon curve. Okay? So actually, the spin 90-degree thing maybe come from this unfolding. That's why I call it the unfolding approach. And the adding a fold to a straight line came from this folding. So okay, so then it's probably convincing that what I have been saying are actually two ways to talk about the same construction. But however, we are not satisfied with this physical hand-waving. We want some more concrete proofs, so which I'm going to show you tonight. And so the way we solve problems in our discipline is to first try to represent things by symbols. And symbols themselves alone are not useful. And with symbols, they should come with properties, laws, rules we can use to manipulate the symbols to find out more properties about the symbols, which I'm going to talk about. But firstly, so how do we represent curves like this? And representing compressing by symbol is a process called abstraction, which I talked about in the class. And in abstraction, we try to figure out what in the phenomena we're describing are actually important to be represented. And in this case, perhaps the actual coordinates of the lines of the dots are not important. The degree of rotation is not important. Or what's important is probably how the curve bends. So then we are going to represent a curve by a sequence of alphabets L and R, where L denotes a left turn and R denotes a right turn. Yes, and it's a bit difficult sometimes, so actually I'm keeping this picture here as a reference. That, okay, so maybe I'll use darker color. Okay, maybe I'll just write black. It's red clear. Okay, black. Okay, so the level 1 curve is just an empty list. There's no band at all. And this one, level 0 curve is just an empty list. A level 1 curve is denoted by an arrow because it's a left turn. Right. And this one, what's this? It's a left turn, and the right turn. So it's denoted by arrow, R. Okay. Now, what about this one? Actually, the beginnings, the prefix are the same. The prefix of the base is repeated. It's called L, R, and there's an arrow in the middle here denoting the fact that you which corresponds to the 90-degree clockwise rotation. And now, what's this one? So it's L turn again. a right turn, and the picture is here, and another right turn. So it's LLR repeated with the arrow in the middle, and the red is LRR. And how was this thing generated? It's okay. This arrow denotes corresponds to the 90-degree turn, and LRR is actually what? When you so this one was this line is the previous curve, and then afterwards you go. Basically, you go. You trace through the same curve backwards, back to the beginning. So. Meanwhile, every arrow turn becomes R turn because you are going backwards. And every R turn becomes an arrow turn. So this LRR is actually LRR reversed with every R turn to L, every L turn to R. So it is denoted by a Haskell program. So right. So now we use a term is either L or R. And we assume a function called inv, which inverts the rotation. L becomes R becomes L. And this unfolding approach, which I'm going to call dragon U, is denoted like this. By the way, I know there are some new friends here today who are not used to the programming language I use. So if you are you don't know the notation, I'm going to explain the notation. But if at any point you forget what this upper notation means, just ask. Okay? So then this dragon U takes a natural number, which is the level of the curve you want to generate. And so the level 0 curve is just an empty list. And to generate one curve of level 1 plus n, you generate the curve, the previous level, by calling yourself dragon U of n, and then this plus symbol, here denotes it's pronounced append, and it denotes concatenating two lists together. And so PS, which is the previous curve, is concatenated with an arrow, and in here you reverse is a function which takes the list and reverts it, and map applies this function into every member of the list. And so that's how this unfold approach is written as a Haskell program. Right? Right. And what about this? What about the other approach, which I'm going to call the folding approach? Well, let's see. How do you model creating, adding an extra fold to every segment? Right. Okay. Again, this is arrow, and the next one is LLR. What's the rule here? So if you look at this picture, okay. Now, if you see the yellow, unfortunately it's yellow. You see the yellow ones first. So this arrow R was the previous curve, LLR. And what happens when you fold the paper like this? Okay. So basically in here, at this point, I'm going to remove the red dots. Okay. LLR. And at this point, because the fold is like this, so you make an arrow fold here. And so there's an arrow and the previous arrow. And here, this one now is an R fold. Okay, this is arrow, and this is R. So because this one is an R fold, you go from right to left, and the curve like this, so it's an R fold. R. Right. And then the previous arrow fold. Now this one, this is our arrow. It's an arrow fold, left fold. Because this is an arrow fold, and this is an R fold. It's an arrow fold. Then an R, then a previous R fold, then an R fold. So basically, what happens now is that you take the previous LLR, and then you insert additional LR between them. Okay. Right. So that's indeed what happened. So this one is actually arrow. This is the previous arrow. This is the previous arrow. This is the previous R, and then you add LR between them. And then to generate the next one, we actually start with LLR, and then interleave LR. And this is the next level dragon curve. And if you check it, it should be the same. Right. So how do you model this process? So is everyone still following me? Are you convinced about this construction? Let's do this again.
What is the relation of this feature and the process you?
You mean the folding one? The unfolding one?
The right hand side.
The right hand side. Are you referring to the new red arrows and LR which I just added? Or are you referring to the previous one? That's make a copy and put an L in the middle and do a map in the reverse.
Left hand side is the unfolding process.
Right.
Right hand side for
The right hand side is the drawing of the folding process. And actually they generate the same sequence.
Yes.
They should generate the same sequence.
So the folding process and there would below.
So you show how you use the paper for each again and again. Right.
No, the right arrow below has
The right arrow.
yellow.
That one. Oh, okay. You mean doing this?
Yeah.
Okay, actually, I mean that I take the black lines is a piece of paper that's already folded.
What is the yellow line?
The yellow line is a fold like this.
Ah.
It's the force I apply to the piece of paper. Try to get it like this. So that's okay. So I'll try this again. That this. So previously, I had a piece of paper like this, which is already folded. And this is the beginning. This is the end. And this is a left turn, this is a right turn. So currently, this if I unfold, if I turn all the angles to 90 degrees, I get a what do I get? This is an arrow. This is an arrow, and this is an R. So now currently the curve is the current curve I have is LLR. Okay. Now this yellow thing is that means that I'm trying to fold this again, like this. So I don't know how to draw this, but now this becomes a little bit like. Okay, now they become a little bit like this. Okay, and this one, supposedly is like this.
No.
This.
Yeah.
Right. And then what are the new things? What are the new symbols I add to the sequence? So the first one is not error anymore. It's not that error anymore. It's this thing. What is this? Is this an arrow or an R? That's an arrow, yes. An arrow. So now an arrow. And now then I continue with the previous arrow. And then later in here, what's this? It's a right fold.
Yeah.
Why is it right? Because actually I'm going backwards. So now under there I'm going from left to right. Now I'm going back from right to left. So now I get right fold. And then the previous arrow fold. And then what about here? This is a arrow fold again. This is an arrow fold. And this is an arrow. Okay. Now the previous right fold. And finally, now again, this is a right fold. So what happens here is that I'm taking the previous line, the previous curve, and add interleave LR into the previous one. And magically, it should be the same sequence I generate with the other approach. Okay? So the task today, no, not yet. So now I have to represent that process formally. So now again, there's another function, dragon F, denoting fold, dragon fold. It's also should be a list of terms. Okay, the types are wrong. They should all be list of terms. But anyway, dragon F is also a function which takes a natural number and generates this term, a list of terms. And when we enter 0, we just get an empty list. Otherwise, to generate the previous level, and then do an LR interleave. And LR, what LR is infinite list. LR is defined by LR is an arrow and an R followed by LR itself. It's an infinite list of terms, which is okay, as long as you don't do induction on it. And this right triangle, which I invented, is which I'm going to pronounce it as interleave. It's like what we usually do, interleaving the contents of two lists, with a slight twist that I'm assuming the left-hand side one to be a infinite long string, and while the right-hand side argument is a finite list. So the blue one has infinite supply of elements. And when the right one is empty, then I still take one element from the left, which corresponds to having an R in the end, and having this red thing in the end. Okay? Otherwise, I take a blue thing from the left and make it the first element. I take a black thing from the right, make it the second element. And then again, interleave the rest of the blue things into the rest of the black things. Okay, that's interleave. Otherwise, okay with that? It's a typical inductive definition. Right. So our task today is to prove that dragon U equals dragon F. How do we do that? By induction. As I said, like I said in the lecture, that's the only way we know how to prove things so far, and we try to use it as much as possible. And okay, to recap, recall that. So how do we prove that? How do we prove the equality of these two functions? And then I'm going to skip several steps and go to the essential properties first. Recall that this one here is simply the definition of dragon U. That the unfolding approach, as I said, that the level 1 plus n curve is generated from level n curve, followed by an arrow, followed by the same level n curve, reversed and inverted. That's the unfolding approach. Okay? And I'm going to skip several steps and claim that if I can prove that the same property, the same pattern holds for the folding approach, from here to here, I'm just changing the black dragon U's to these red dragon F's. If I can show that the same pattern holds for dragon F, then they are the same function. And there are several ways to argue that, but one of the ways to say that is that these recursive definitions are unique. So there should be only one function that meets this pattern. Well, if another function also had this pattern, they have to be the same function. But so now this property is what I'm going to prove later. This looks complicated and very long, but it doesn't matter because from now on we'll try to work on the symbols and let the symbols help us. But firstly, okay, let's recall that. Recall proof by induction. Just because also it's probably also a problem because we just spoke about in the course that how do we prove it? Assuming that there's a property, some property P which holds for which is a predicate on natural numbers, and I wish to show that this property holds for all natural numbers. How do I do that? So one of the ways, actually the only way we know for proving such property is to use mathematical induction, and which is, so what is that? Think about, try to recall that in your mind for 10 seconds. Okay, so to prove a property holds for all natural numbers, it is sufficient to show that, firstly, it holds for 0, and secondly, if, assuming that it holds for some natural number n, it also holds for 1 plus n, for all n. If these two things, if we can show these two things, then we can claim that this property holds for all natural numbers. Now, the thing we are proving is this crazy expression with n as its argument. So basically, we are going to, I cannot easily erase it, right? Good. Okay. So basically, what I'm going to do later is basically letting this P of n be, let P of n be this property. And so we're going to show that this holds for n being 0, and also try to prove this property for 1 plus n, assuming that it holds for n. Okay, and the 0 case, we're going to skip it because it trivially holds, right? And the left-hand side is 1, the right-hand side. Both sides reduced to one single L. Okay, so the case for n being 0, E of 0 is simply true. And then now we are going to prove, here we're basically trying to prove P1 plus n, provided that we pretend P of n to be true. And that's actually proving that this one, smaller. That's actually proving this one equals this one. So it's the same property with 2 plus n instead of 1 plus n. Here it's 1 plus n instead of n. Okay? Right. You all okay with that? Okay. What should we do now? I don't know, so let's just unfold the definitions to see whether there's anything clever I can do. So, according to the definition of dragon f, we call the definition of dragon f. Dragon f of 1 plus n is simply LR dragon of 1 plus n is LR interleave of dragon f of n. So, dragon of 2 plus n is LR interleave of dragon f of 1 plus n. Right? Okay, that's just the definition. Now what? Okay. Anyway, but now we have dragon f already, 1 plus n already. Right? So let's use induction. Pretending that this property holds. So LR interleave. And now dragon f 1 plus n by induction equals dragon f n append an arrow and map int of reverse of dragon f of n bracket. Yes. No, another bracket. Right. Then what? Think about what we want. Okay? So as I said in the class, basically in a derivation should always have a purpose. You don't calculate blindly, try to hit something by luck. There should always be a purpose. The purpose now is that we eventually want this expression. And this expression is what? This is actually LR interleave dragon f of n by definition of f. And that one is, what's this? Is by definition, this one is LR interleave of dragon f n with something underneath. So now, if we manage to bring LR interleave next to dragon f, we can fold them back by the definition and get the expression we want. So now the purpose is to try to distribute LR interleaved into this expression until they reach dragon F. So now I'm working by the symbol. Actually, I'm not thinking about what this all means. That's too hard for me, thinking about meanings of things. And now I'm only capable of manipulating the symbols and try to set a goal according to the symbol. So the symbols help me. The symbols are working for me now. And now the purpose is try to move LR interleaved into the expression and try to reach dragon F and see and try to reconstruct this dot part. If we are lucky, we get the expression we want. And so the reasoning I get just now, I was thinking syntactically. And also now I'm again thinking syntactically. So to move LR interleaved into the expression, what properties do I need to know? Because in the expression, the outermost, what are blocking me? What are stopping me from moving LR interleaved into the expression? So the outermost operator are these appends. So I want to think about what happens when LR interleaved touches append. And what can that be? So maybe I should think about things like, okay, when I have an LR interleave with two lists append together, then what happens? Is there a way to allow me to move LR interleave closer to x's and y's? I need some properties like this.
Length of axis.
Sorry?
You need length of axis.
I need what?
Length of axis.
Yes. Length of axis. Something like that. Yeah. Right? Eventually, so usually I've been thinking syntactically so far, but then now I come back to semantics. And then think about, well, actually, what does this mean? What does it do? What can possibly be true, given what I know about what LR interleave does? Then it turns out that the property I have is actually this one. That, okay, LR interleave of x's append some z's in the middle, and y's, equals the next one, where LR interleave is distributed into x's, next to x's and y's, still with the same z in the middle, provided that axis has an odd length. If the left axis is even, then that one has to be our LR interleave, but we don't need it today. Do you believe that? Let's see an example. Okay. So assuming that axis is ABC and the y's is BE and the z is the yellow thing in the middle. So if we just do the distribution, what do we get? We get ABC, Z, BE with LR interleaved. We take it apart and we take it apart, disassemble it into three lists. And indeed, this one is LR interleave ABC, and this one is LR interleave BE. Okay. So in this case, I'm allowed to distribute LR interleave next to the two black lists. Okay. Do you believe that? And of course, this is not a proof. This is just an example. To prove this property, okay, this property needs proving, but it's just a matter of a single induction. I submit this work to a journal, and the referee said, "No, this is not a simple induction." And that referee was very. I'm happy that he or she was very interested in it. So they spent lots of time producing exact proofs of this. I was very moved, but actually it's really a simple proof. So then I did my exact proof as well, which is much easier. I don't know. Anyway, and yeah, it's just a simple proof. Okay, so and also this property applies only when axis has an odd length. But luckily, a dragon curve always has the dragon curve always has an odd length apart from the base case. Right? The base case is a length 0, then a list of length 1. Then you always duplicate it and add one thing to the middle, so the length is always odd. That's also an inductive proof. And every proof is an inductive proof because that's the only way I know how to prove things. So, right. So let's see. Now this one has an odd length, so I can safely distribute LR next to dragon F. And with the L in the middle, with LR interleaved here already, and finally, wow, map in. To be clear, I will add a bracket here, although it's not necessary. Map in of reverse of dragon F of L. Right, okay? And good news is that I have this already. Okay, that's a good sign. Then now, okay, I will try harder. Try to move around closer to here. Okay, there's still 2 steps to overcome. Now, what happens when LR interleave means net? In particular, net means right. Okay, LR interleave has this naturality property that you should have this naturality property that if I have 2 blacklists, Z and X's. If I do F to everything Z, and also do F to everything X's, and then interleave them, it should be the same as just interleave them, and then do F to everything, right? Yeah. And it's actually a free theorem. Okay, that's a technical term we use. And however, what we have is slightly different. There's no net F here. It's just LR. It's just an LR. So, but what actually happens? Maybe. Okay, maybe we can do this, saying that LR interleave, and also in our particular case, this F is not any F, it's int. So int have this property that if you do int twice, let's call this twice, you get the same thing. So it's actually, okay, to mesh the pattern on the left-hand side, I'm going to do a map-inv of map-inv of LR, which is still LR. Interleave map-inv of axis Then, according to the left-hand side, now this one is map inf of LR interleave what am I doing here? Is this what I did? Let's see. No, this is, sorry, this is the map inf. Map inf of axis. Oops. Axis. Of Y's. Yeah. Just I'm calling Y's. Okay, so actually it's the same as doing one single map inf. I am undistributing this to map into the outside. Yeah, that's right. And in the inside, I have what? I have map inf of LR interleave once. Okay. This is triangle once. Right. Which is the property here? And in this, in the main calculation, Z is LR, and the map in Z is actually RL. But however, we don't need that much today. So okay, back to this calculation. I'm copying this dragon F of n, the pen arrow, which is the same. And now, what do I have? On the left hand side, I have LR interleave outside, and now I can extract and map inf from the expression. And now, LR gets pushed into the expression, but I'm slightly worrying that now it's not LR anymore, it's map in LR interleaved into reverse. Okay. So LR interleaved because map in LR interleaved. Slightly worrying, but maybe it doesn't matter. And now, in final step, let's think about what happens when something is interleaved into the reverse of a list. If the list happens to have an odd length, then, okay, then this one holds for LR only. On the right hand side, I am taking the inverse of LR, which is RL, but interleaving that into the reverse of axis. It's the same as interleaving LR into the list and then take the reverse. To convince you that I'm doing this proof by example thing, which is not right. But, okay, assuming that axis is ABC, if I interleave LR into ABC, that gives me LA, RB, LC, R. And then I revert it. I get RC, LB, RA, L, which is the reverse of ABC with the inverse of LR interleaved into it. Okay? And that is a proof, but that's also a simple proof. This property needs the first property. Right. So, and this one happens to be the property I already have. So, that gives me, okay, that already gives me this, I hope. that this is and with arrow in the middle, and here I mapping stays here, and here I get LR interleaved into RL interleaved to the reverse of a length having an arc length, which is actually doing the reverse outside and extracting the reverse outside with LR interleaved into dragon F. F of N. Which is what I want, because this one by definition is dragon F of 1 plus N. And this one by definition is dragon F of 1 plus N. So we are done. And yeah, then I used about an hour, so I will stop here. There's a generalization of this, which I'm going to briefly talk about. Then just in the construction, I always do this 90-degree clockwise turn, which is a bit too specific. Then of course you can easily generalize it by allowing one to do not only clockwise turn, but also counterclockwise turn or anti-clockwise turn. So in the generalization, instead of taking a number, the generalized dragon fold, takes the dragon unfold takes a list of instructions. So use the previous version of dragon view takes a natural number, but now it takes a list of rotations. Each rotation is a counterclockwise turn or an anti-clockwise turn. And so when it's counterclockwise, we do the same thing. When the first instruction is anti-clockwise, we do a right turn instead. Okay? And that's the generalized unfold approach. And the generalized folding approach has to deconstruct this from the right end. Okay, yeah, it makes sense, because you're unfolding from one end, so only after you have folded from the right from the other end. So the first thing you unfold is always the last thing you fold. So you need to go from the right from the other end. And then when the last instruction is clockwise, you do the same thing of interleaving LR into the list. When the last instruction is anti-clockwise, you interleave RL into the list, when RL is RL, etc. And so this generalization, I'm going to show you some example here that according to, this is probably from, I think it's from an early paper of Toulouse. If you do clockwise, anti-clockwise, clockwise, anti-clockwise, alternatively, you get a triangle like this. And this one is also from the paper of Toulouse, is the picture you get from this sequence of instructions. They call it big bear, middle bear, small bear, or three bears. And so yes, and still we can prove that the these two constructions are the same. But just very quick, I'm just going to go through very quickly. Raise your hand, you know what a fold R is. Okay, and raise your hand, you know what a fold arrow is. In flow lab, we didn't talk about fold arrow. And fold R is folding, bracketing from the right, and the fold arrow is folding from the left. Anyway, dragon U is a fold R, and the dragon f is a fold arrow. And to show that, so to prove that they are the same, actually I recall that there's an old theorem from an old textbook giving a condition when a fold r is equal to a fold arrow. Basically, okay, the argument of fold r is the yellow one, and the argument of fold arrow is the purple one, and the fold r equals the fold arrow if by this thing called the second duality theorem, the fold r equals the fold left, if this property holds. And this one basically says that the yellow thing and the purple thing, when mixed together, can be swapped, or they are kind of associative. You can move the brackets around, and that allows you to turn a rightmost, say right associative computation into a left associative computation, blah, 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 blah. But then to prove that, if you expand the definition, it turns out that you will be proving exactly the same properties that I proved now. It's just sometimes right, sometimes left, but actually it's exactly the same property. So we have proved general case already. The referee also complained about this. How does it improve to me? Yeah. So that's it. So what did we do today? We talked about dragon curve as an excuse to talk about inductive proofs and about what I think about manipulating symbols. That so about how we solve a problem. We try to model a problem by inventing symbols for it. And then symbols alone are not useful yet. We have to think about what properties they have. That allows us to think, to look at expression and think of it in terms of, and think of it by syntax. From the syntax, we invent properties we might need to meet our purpose. We always have a purpose. When doing proof, there's always a purpose. And then we sometimes go back to things semantically, to guess what properties are possibly true. That also what properties that may be useful to us are probably true, and then prove them afterwards. Because in proofs, I was often asked this question: how do you know that you need to use this lemma? Usually, my answer is after years of working on it. In the first few years, I would think, just experience, do it long enough, and you will know. But later, when I think about how I work, is actually think about the syntax and try to guess what you need. There's always a bit of luck in it. But however, because you know that you have a purpose, so you will not go too wrong if the property you are proving is right. That's all. And then you prove the lemma afterwards by following the same principle. Okay? So yeah, that's in our small niche community. The slogan we like to say is to let the symbols work for you. And with things like distributivity are your friend, associativity is your friend, and you use that a lot to prove properties. And expressions are your friend, because once you can write things down like this, you have solved half of the problem. Okay, I think that's all I'm going to say today. Thank you.都是问也可以。
那个 make 跟三角形跟的性质，
这个吗？
一个 make 是 string 的
yes。make
是 list。
yes，没错。
虽然好像 type 也 OK 啦，但是
对，其实它们是不一样的 maps，they are different maps。 So this one is the map for strings, and this one is the map for lists. And whereas, what about this? This one is the map for lists. Yes, that's right. That's the right observation. So I'm simplifying things here now. However, basically, this is the naturally property of interleave, which comes from its type. Have you heard of naturally, or free theorem, or another terminology they call this is parametricity? That basically this comes from the fact that this interleave operator has type string of A to list of A to list of A, right? And for all A. And so this for all A is important in this case because interleave has to work for any A, whatever it is, which means that interleave cannot inspect each individual element. So all it can do is moving things around. So which means that if you do the same thing to every element of the string or list, doing the same thing add to every element of the string Z and the list axis doesn't change the way how the yellow part of the interleave behaves. So that can be safely extracted. But in general, when we model this property, if the type is string, then we use the map for string. If the type is list, then we use the map for list for lists. And assuming that we have a function called flatten, which takes a tree of A and flatten it to a list of A, then the corresponding free theorem is that if you take a list, take a tree, do a map tree to every element. Do F to every element in a tree before flattening it. Is the same as flattening it first, and do the same thing F to every element of the resulting list. So yes, the map you use come from the type. Yes, those are different maps. And there's a lot we can talk about. I think we talked about free theorems in functional Thursday before, but if you like to listen to it, I can talk about it again. Any other comments, questions? U 有一个 equation 是this 这样吗？还是说是这个？还是说是这个？这个。
那虽然 proof 的下面有一个 this， 但是好像还没有讲说这个 equation 也只有一个，所以有点那个。
你说还没有讲说这个 equation
只有一个 solution。
right. So firstly, so he was asking. I haven't discussed the fact that functions satisfying such equations are unique. Actually, so firstly, because it's because this is an induction. So in the first line, with black dragon U's come from the definition of dragon U. And you see that this is a nicely well-founded inductive definition where you start from 0 as the base case, and the case for 1 plus n is built on the case for n. And then definitions having this form are good definitions in the sense that there's a unique solution satisfying this. But it's the same, like you might remember that, say when because this is just the 4-dimensional numbers, and so like when I define things like sum of lists, sum of empty lists is 0, sum of x constant x's is, assuming that you know how to compute sum of x's, you do another x plus. And also this definition is a good one because you have a base case, and the inductive case is built on the definition of the same function on the substructure of it. And again, so this definition has unique solutions. And but here I'm just repeating the fact. Probably that doesn't give you much new information. However, maybe does it help if I show you how this actually works? So, assuming that now I want to prove dragon U is dragon F, I said I skipped some steps, which is actually like this. I want to prove that dragon U is dragon F by induction. Okay, so then I start the base case dragon U of 0 equals dragon F of 0 is immediate. Both are empty lists. Okay, now dragon U of dragon U of 1 plus n is what is by definition okay. But dragon U of 1 plus n by definition is dragon U of n append error, append map of in of reverse. I'm going to write ref to be shorter, of dragon U of n. Right? Then by induction, dragon U is dragon. By induction, dragon U is dragon F for numbers smaller than 1 plus n. So now this dragon F of n append U stays unchanged, append L stays unchanged, map in stays unchanged, and ref of this is dragon F of n. Okay. Now, if I can show that this is dragon F of n plus 1, of 1 plus n, so then we are done. And then this equality is a property I want here. So that's another way to see that. But I skip this to make it go shorter. Right. Okay. Questions, comments? Or listen?
What's the first duality theorem? That's the second one.
Well, I think the first second duality, first duality.
Google.
I know several homomorphism theorem. The second duality is this. I think the first is probably related to. Oh, I forgot. I need to check.
Okay.
Yeah, I need to check. But anyway, it's something related to both rights and both lefts. And yeah, but what else are more important about than this, about both right and both left? I don't know.
So we say every data structure, every inductive data structure has its pole. So does every inductive depth structure have there for the F, or is it specific to this?
Yeah, that's a good question, and it has been that's a good question, and one of my colleagues actually is another student of my supervisor, Jeremy Gibbons. He wrote a lot about it, and so he tried to generalize fold left to trees. And in the case of trees, okay, the lists are singular. Fold right goes from right to left, goes from brackets from right to left. Anyway, so the bracketing is the same as how the data structure is built. And fold left goes the other way around. And for trees, then it's more about subtrees and paths. So the fold which you naturally induce from the data structure recursively operates on the substructure before doing the folding. Whereas the equivalence of fold left on trees operates on paths. So it goes to the end of the path. No. You pass the information from the top, then which goes to the end of the path. So something like that.
So it's like DFS on trees.
I'm not quite sure. I think DFS is more specific than that. So it's another operation. Also, it's like fold passing information from bottom up, and fold left for trees passing information from top to bottom. So it's not quite like the depth first search, and it doesn't always it doesn't generalize nicely to every data structure. But however, I think it's a nice work of it, so which I can try to find for you. Anyone want to say something?
Well, I looked at what the first duality theorem is.
So that it
So it's the conditions when left fold, right fold are equivalent when they're applying the same function.
Can you just say again?
Well, you can see, I mean, you're using two different functions with fold left and fold right.
Okay. So it's when fold R equals fold left.
With the same thing.
Provided that this
It's associative and has an identity
associative.
element. Associative and has an identity element.
Yeah. So also you want E plus X be the same as XO plus E. Do they have? Yeah. It doesn't have to be E, I believe, definitely not. And also you want XO plus Y plus Z to be associative. Right. Thank you. Yeah, that makes sense. It makes sense as the first error before generalizing to something crazy like that. Thank you.
I'm not sure that I totally followed the generalized dragon function. Is it starting with a different initial, like an arbitrary initial curve? Or like how is it modifying it?
Oh, you still start with the single segment as the base case. So the base case is still the empty list. But then.
So it's a different amount of rotation. What is the thing that you have freedom over?
You have freedom of rotating clockwise or anti-clockwise. In the previous dragon U can be think of as a special case where every instruction is C. So you get now you have an input which contains only C's. So now the C doesn't have information. It's actually just a natural number. And so when the instruction is C, you do a clockwise rotation using L in the middle. But now the generalization is that you can also sometimes rotate counterclockwise.
I see. So you have to supply a decision for every step.
Yes.
So like if you want a 10th level, you supply 10 decisions.
Yes.
And then okay.
Yes, exactly. So I think this picture comes from, I think it comes from that end actually. So it comes from doing A is anti-clockwise turn, then do a counterclockwise turn, and then do a clockwise turn.
So this is like if you took your folding paper, you decide which way to fold it each time, and that's the sequence.
Yes. Yeah.
Yeah.
And then also interestingly that so in the case of natural number, it doesn't matter where I start because adding one from the end from one end is the same as adding one from the other end. But here actually if dragging U is defined by extracting the leftmost instruction first, dragon F needs to be defined by extracting the rightmost instruction first. And then they will turn out to be the same. And the proof is actually the same proof. I said it's the same proof.
If you start with something other than the empty list, do you get similar curves?
I don't know. I haven't thought about it at all. And one funny thing would be that if the base case is something other than empty list, I might lose the property that I always get the list of odd length. Then maybe some properties do not hold in the middle, so then I'm not sure what I end up generating. That's interesting.
If you start with an odd length,
It's always going to be that all but the first one are all.
yeah, only in this case, only the base case has a even length. Yeah. Yes, but anyway, because if I do that, I always get the odd length. Okay, good. So maybe some properties still hold. Still, I don't know what I'm generating. But could they still? Yes. Actually, I don't know what I'm generating, but still, the two functions still generate the same thing. Good. Good news. I can play with it. Thank you. Good.
Could you switch it to a one portion or a dragon curve feature? Like you say, three variables.
Okay.
I'm curious that this three variable, they look smear right. Does it have the property that maybe 它们三个是同碎形之类的东西？
You mean
看起来相当是
Yeah. You mean
只是一种直觉上的
the
影
whole
响。
the pictures are no, so sorry. The pictures are composed of self-similar
Yeah.
I think that still holds because basically this picture is still generated from itself just by different rotation. The case for the this is my paper by the way. By the way, so actually I need to credit my co-authors that so this is me, and then actually Zhang Pingwu is our intern 2 years ago, a very smart intern. He came up with this topic, and then so then I find it very fascinating. So I encouraged him to develop it and make it a paper, and so then Liang Ting was his supervisor. So I can talk about his thanks to them. And okay, this in the case of this one, it's more obvious because basically you generate this picture by this picture was generating from two copies of itself, and I'm not sure where to cut it in the middle. Maybe somewhere like this. Definitely wrong, but okay. And Then there are, but in the more general case, it's still the same picture, but maybe rotated to the other side. So they can still be decomposed into smaller parts that are the same modulo rotation. And actually, there's another. So actually, you can create 4 copies of it. So you can make another copy here and another copy here. Then these 4 copies end up filling the space. So that's another property of this thing, which I haven't carefully studied yet. Knuth has a paper, has a chapter of a book on dragon curves. Seems like he likes dragon curves a lot. There's a video of him in his home being interviewed. He has a sculpture of dragon curve on one of his walls. So he likes this very much. And he has a chapter written about this. So he started with the same construction I have, with the 2 approaches. Then he quickly moved on to comparing this with a kind of number representation. Then he talked about complex numbers. I don't know why. So I'm going to ask what my interns this year to study it, and hopefully ask him to explain this for me. And then he used these properties about complex numbers to show that the curve doesn't cross itself. And there are lots of interesting things. And so also, if you're interested, I can also show you that chapter. Maybe I can put the information on our Slack. Yeah, we can use it. We should use it. Okay, I think it's about time to start our free discussion session. So thank you for your enthusiasm, and hope you find it